Hey everyone, how's it going? I'm Matt here with a quick video on stacks, queues, and heaps. In particular, this video is on a common technique that uses heaps, which is the top k elements technique. So in this technique, you're given a list of elements and you need to return the highest k of those elements. You can also use it to obviously return the least k, and then there's some spins to this problem or this technique, right? But this idea of returning the k most and the k least is all over the place. So, um, without further ado, I am going to jump in to my notebook and kind of explain this problem and how you approach it, right? So you're given an array. Here you're given 5, 1, 4, 10, 2, 3, 7, whatever. You're given a number k, and so you have to return the three largest elements in this array. So if we just look at it by eye, we know that those are 5, 10, and 7. Okay? And to make sure that this video kind of goes faster, I wrote the pseudocode for a very trivial solution to this problem. Right. So, and I think with enough thinking, most of you will come up with this, is you start off with some list, right? So this is going to be a result list, right? And you go through every single number in this array, right? If there's, if we still don't have k elements in the list, just add that number to the list, right? So in the case of k equals 3, right, we would go for 5, 1, and 4, we would just add it to the list, right? Otherwise, if the number is greater than the minimum that's in that list, replace the minimum with that number. And so this might be really confusing just looking at it right now, but let's run through an example. So we start off, we look at 5, right? And our resulting list, this is going to be a result list, and we see, okay, we don't have 3 elements yet, let's just add it to our list. Then we look at 1, same thing, we don't have 3 elements list yet, just add it to the list. Then we look at 4. Again, we don't have 3 elements yet, so let's add it to the list. Now, we look at 10. And we already have 3 elements in our list. So, if 10 is better than any of these elements, right, then we have to replace that element with 10, right? 10 needs to take its place. So in this case, 10 is better than all of the elements, right? But you need to just replace with the minimum one, right? Because why would I replace 10 with 5, right? 5 could be in the top 3, but I know that 10, about that 1 is surely not in the top 3, right? Because we just found, it just got kicked out. All right, so we replace that 1 with 10, right? Then we look at 2, but now 2 is not larger than any of the numbers, right? And it's enough to just say 2 is not larger than the minimum of these numbers, right? Those are the same thing, right? So 2 is not larger than any of the numbers, not larger than the minimum of these numbers. So we don't do anything. 3, again, not larger than any of these numbers, but 7 is larger than both 5 and 4, right? So we replace 7 with the minimum, which is 4, right? So 4 gets kicked out is the way I like to think of it. And now we have our top 3 elements, which are 5, 10, and 7, right? So this is an approach and it works, right? It's a very straightforward approach. It's nice. But let's talk about the time and space complexity now, right? We have an outer loop here, which is O of n, right? Now sometimes, in the best case, for the first k elements, you you're just adding a number. That's nice, it's constant time, but that's not the general case. The general case for the rest of the numbers is we take that number and we have to check whether the number is greater than the minimum of the numbers in the current result. And finding this minimum, if I have a list, this is going to take O of k time. I have to loop through this whole list and find what the minimum number is, right? And then I replace, and this is going to be O of 1 time, right? Up here, that was O of 1 time as well. But whatever, we don't really care about that. Those are constant time operations. So we have an outer loop that's O of n and an inner loop that's O of k. And so that gives us our time to be O of n by k. Now our space in this case is just an output list. So it's just going to be O of 1. Sorry, I was going to write O of k. It's just O of 1. Because it doesn't make sense to add to consider the result as extra space because you need that to answer the problem, right? You need to make a list that size k, right? So you're not using any more space than you need to, is what this O of 1 is saying, right? All right. So now we want to think about how can we optimize this, right? So there's really two parts to this time complexity. There's the O of n part and there's the O of k part, right? The question I always like to ask is, can I do any better, right? So for this outer O of n part, can I do any better than O of n? Well, logically, no. You can't do any better than O of n because that would imply that there's, some way of ignoring some of these numbers, right? Like I can say that, anything better than O of n for this loop means I can ignore some of the numbers in the array. And that doesn't make sense, right? Because we need to look at all of them to know what the highest is logically. There's no way for me to just arbitrarily say, for example, half of the array I can just ignore. I don't have to look at them, right? So this O of n is necessary. We can't have a solution that's better than O of n, right? Just in terms of logic. So now the question becomes, how can I find the minimum in better than O of k time, right? And this is where the heap comes into play, right? So if I have a min heap, let's say, what if result, instead of being a list, we make this a min heap, right? Then this becomes O of log k, right? And actually, our constant time, everything we're doing here becomes O of log k. So we have a bunch of O of log k operations, right? But our space complexity kind of goes down to O of n times log k. But in this case, the data structure we're using is a min heap, right? And probably the question wants you to return as a list. So at the very end, what you need to do is you need to take everything that's in your min heap and dump it into a list, right? So that's going to be O of k space, right? Because now the intermediate data structure that we're using is a min heap. We can't just return that. Before we were using a list, so we could just return it and we're not using extra space, right? But this is actually pretty good, right? We just reduced to from O of nk to O of n times log k, and you can consider that if k is a really, really big number, this scales a lot better. And the space complexity is definitely something that you'd want to mention to your interviewer, right? But it's not that big of a deal, right? In general computing, right? O of k, using some space to save some time, that's actually pretty great. Like we have more space, like we're more constrained by space, by time nowadays than we are by space in a lot of applications. It's not always true. Embedded systems, it's not the case. Like mobile computing is also often not the case, although that's becoming less and less true. But yeah, so the space complexity, it's a trade-off there, and you could discuss it. Now, I want to hone in on the fact that we said that, you know, we would end with some heap, right, that kind of looks like this, and we would dump that into a list, right? Oh, whoops, actually it doesn't look like this. It looks like this. 5, 10, 7. It's a min heap, right? Because we're doing the min operations, right? So every time I'm going to extract min and dump it into the list, so I end up getting the output in sorted order. Before, this was in the order of appearance, right? In the original array. So 5, then 10, then 7, because it's the order they appeared in. But now it's in sorted order. Okay. And actually, if what the question is asking is to return the list in sorted order, then the O of n log k solution is the best we can do, right? But if it's not sorted and it's just asking for the top k elements in arbitrary order, interestingly, you can you can do the top k operation in O of n time. Okay, so there's actually an algorithm where the best case is O of n time, right? And this is called quick select, right? Or Hoare's algorithm. All right, and I really suggest that you look this up, but this is more relevant once we get to the sorting section of this of the curriculum, because quick select is actually a modification of quick sort. Okay, and that's a well-known sorting algorithm. All right. So the point being that for top k elements, if the output is asking for the k elements in sorted order, then this approach using a min heap is the best possible. But if you don't care about whether or not they're sorted, then you can actually use quick select to do things even faster. And that's in O of n time and O of log n space actually. Um, so that's pretty neat. Now I'll leave as an exercise to you translating this algorithm to do it for the least k elements, and that should be pretty straightforward once you go over this.